And we are next at the test for independence. So the first one is the test of the goodness for fit test. This one is the test for independence. And let's see what it means here. Again, XKCD comics, because we all love that. This is another classic question about statistics for the correlation versus causation. Okay, so what this comic is trying to explain is, we believe you may have seen this if you use Line or any social media. You may have seen this claim that cell phone causes cancer because you have cell phone, and this device, this mysterious device that no one knows about, right, has some radiation from the phone through our brain to everywhere. And so people believe that if you use cell phone too much for too long, then it will cause you cancer in your brain. Or actually, everywhere it touch. If you put it in your pocket, you may have like a leg cancer or whatever that. This comic is making fun of that idea and just reverses, right? If you have the trends for two different categories, right? You may claim that one cause the other, or the other way around. And so in this case, the guy with the hat is claiming that actually the more cancer patients there are, the more cell phones are produced. Right? It can be the reverse. Right? That's the gimmick here. Right? If you claim one cause the other by just a single graph, if you look just at a single graph and claim that, then you can easily claim the opposite. And also there are problems with the axis. This one uses 500, 0 to actually like 400 to 500. The other one is 0 to 100. The right is percentage. The left is per 100,000. Again, there are so many problems with this graph. If you're not careful enough with what you are trying to say. Okay. So the question is, yeah, we have a set of data, and we wanted to see if the two different categories are related. Also, common, let's say, misconceptions are like you may claim that the ice cream cells is caused by the heat stroke. Because in summers, you see that in summer, like, people buy more ice cream, obviously, I think, and also more people get heat stroke because it's so hot. Okay. And if you just look at the graph, right, or the graph or the table or whatever media you are more comfortable with, you may see this kind of frame. And you may make this kind of claim. The question is it true or not, right? And now we are trying to answer it. Yes, we can use chi-square test to test some of these claims. These claims are in one of these form. So we are trying to find the relationship between one category and the other. So and we have to go back one step. We have to first see if they are related or not, and then afterward we can use different tools to test whether one causes the other or the other way around. Right. So we are dealing with the first step to see if these two categories are related or not in the first place. To see that, we make a table here. Okay, so for the first category, we have item 1, 2, 3. Maybe the first category is age range again. So let's say like child, teenager, adult. I know that's a big gap, but let's say child, teenager, adult. Okay. Maybe the second category, you believe they have different preference for, let's say, ice cream taste. They say that's chocolate, vanilla, and what else? Green tea. No, just because. Maybe you just like use your intuition and say, okay, children prefer chocolate, teen prefer vanilla, and adult prefer green tea. Something like that. And the way to test whether what you believe is true or false is to use this table. So we do a survey on people. Maybe we have like 100 children, 100 teenagers, 100 adults, and we ask each of them what ice cream flavor they prefer. Right, and then they will give us this number. Maybe let's say like 50 children prefer chocolate, 30 of them prefer vanilla, 20 of them prefer green tea. And we repeat that for the teenagers. Maybe here only 40 of them prefer chocolate. And then, I don't know, 10 of them prefer vanilla and 50 of them prefer green tea. And we repeat that again for adults. And we may get something like, let's say 20. 60, 20. Right. So we look at these numbers and we want to we want to see if they are related or not. Before we go into the details on how to compute the numbers, right, let's go back and say if what would happen if this is this is evenly distributed. If we leave that 1/3 of the children should prefer chocolate, 1/3 of the children should prefer vanilla, and 1/3 of the children should prefer green tea. And that's the same with the teen and adults. Right. So maybe we may believe that these two categories should not influence the other. There should be no preference toward children. There should be no preference toward teen and adults. And also the other way around. There should be no difference toward green tea or vanilla or chocolate. That means what we would expect here is if we survey, let's say 90 people, we should expect like 30 in each category. Right? If we believe that these numbers are independent, CTA, okay. Then we have like CBG. Oh, sorry, again my head is getting in the way. Right. This is the table that we expect to see if we survey how many? 227? If we survey 90 people in each age range. But sometimes we cannot get that nice table because maybe we are near school, so we get more kids but fewer adults. So maybe you can survey, let's say 300 children, but maybe only 90 teenagers and only 60 adults. Yeah. And that is and that is fine. But if we really believe that they are different, then out of these 300 children, we should expect to see. Oh, I can change color. That's first time. We should expect these 300 to be evenly distributed between these three different flavors. Right. And again, repeat that for teenagers. If we survey 90 teenagers, then we expect to see 30 in each category. For the adults, we expect 20 each. Oh, by the way, it's raining out there, so my face would look like a little bit darker, but we are fine here. Okay, so if you believe that age range, we have two categories. We have age ranges and ice cream flavor preferences are, it's the keyword independent. Okay, that's a keyword here. If you believe these two are independent, we should see this nice table. So what we are doing here, we are trying to use our ideal expected outcome and compare that with the observed outcome from the samples that we got. And so we, here we have the formula here. So okay, sorry, that's a fancy one. We have a summation inside the summation. That's the double summation. That means we sum across J from C. We take a sum here. Okay. That's one single summation. And then we take multiple summations. So this formula is describing. We take the sum of the sums. And as you can see, that is exactly the table we have up there. Okay. So what we are doing here is let's just look at the formula. Right? This is the minus sign. That means we take a difference between what? Between the observed and expected counts, right? O and E. We take a difference and then we square it so that we get a nice value. We compare the observed one with the expected one. That has nice numbers in each categories. Okay. And we take a sum across all the entries. We just again sum them up, and that single number is the chi-square we want. It is just describing that in details on what each OI is, and what each EI is. Sorry, what each OI is and what each EI is. Right. And for the chi-square, we have to also specify what is the degree of freedom. What table would we have to look at? I'm looking here. Okay, better, more light. Right, that's the just take we take the R minus 1 times C minus 1. R is the number of it's not here. I is the number of rows. In that case, it's the ice cream flavors, and C is the number of columns or the age ranges. In our case, so for example, if we have a table of two, if we want to perform a chi-square on two categories, where each category contains 3 different items in each. Right. That would give us 9 entries to sum here. But for the degree of freedom, we only have 3 minus 1 times 3 minus 1, which is 4. 2 times 2 is 4. The degree of freedom is 4. So you are going to need to look at the table for chi-square where df equals to 4. So that's the idea for the chi-square. Sorry, for the independence. Okay. And actually, let me go back and correct. There. This is one way we can use the test for independence. If we believe that each category, each ice cream flavor is equally likely. In this case, we believe it is 1/3, 1/3, 1/3. Yeah. But we can also use that where each of these proportions are different. For example, we believe this is, let's say, what's a nice number? 1/3, 1/2, 1/3, and 1/6. That's one nice number. So we have 3 different items in the first, second, and third category. And then we may know from other surveys or from experiments or from whatever that they have different numbers of, they have different proportions. Just as before, if we take a survey around middle school, we expect to see more children than teenagers and more teenagers than adults. And this is the same here. We may expect this. And again, for the ice cream, maybe we expect something else. And we know that people prefer green tea for, again, whatever reason. And less people prefer chocolate just because. Or vanilla or whatever. Yeah. If you have these 2 different categories, right, if they are actually independent, you have to go back to the definition of independence. We have events A and B. Right. If you believe that these events, the event A and event B, are independent, then that's the let's start the union. The intersection. Yeah, the intersection of these 2 events can be computed by taking each probability and multiply them. So again here, if you believe that the event A, like the age range, are independent to the ice cream flavor, then we can get the ratio, the proportion for each entry. So if we leave 1/2 is here, 1/2 is here, then this is 1/4. Just multiply them up. If you believe it is 1/3, and that is 1/2, we have 1/6 here, and then that's 1/12, and then we repeat the whole thing. So if this is what we believe, 1/36, like, we should expect this ratio. Okay. And then from that ratio, if we scale it up by the sample size, then that would be this thing that we have here. Oh, this is black. This is this thing here. We sum the R, the size of the row and the size of the columns, and divided that by the total number of people of other samples. But the thing is, the numbers up there, these 3 numbers, we don't even need to specify that. It can be anything you want. Oh, sorry, it can be anything. We don't have to know that exactly. Let's just say, oh, and let's say P1, P2, P3, right? If these 2, the green and the pink categories, are independent, then the result, the table we have below, should be the product of each of the numbers. So that's I think that's the independent test. The statement, the null hypothesis, is that the 2 classification the two classifications are independent of each other. Right. And the alternative hypothesis is that they are not independent. Right. Or if you may say that they are dependent. These two are the same, but just like slight difference. It depends on what context you are talking about. And so that's it. So we still have it. After we construct this nice table, we can just use the same formula for chi-square. We sum them up and get the chi-square and get the p-value, and then decide whether that p-value is too large. That's the second one. Yeah, let's go to the next one then. The test of a single variance. So the thing is, we have learned how to conduct a null hypothesis testing for mu. Oh, another one. Mu and p. Right. But we have the three main things. If you remember, we always see these three friends together. We see the mu, p, and sigma, or sigma square. So we can test the first two, but we could not test the last one. The reason why we can't, because the last one is not normally distributed. Why are they not? Because the variance is chi-square. Oh, sorry, the variance is in the form of the zeta square, and that square is not linear. So we cannot. So the variance doesn't agree with the rule of large number and the central limit theorem. If you expand that out, we get the summation of xi minus x bar square divided by n. Yeah. And that square is not normally distributed. The mu is normal. The mu. The average is normally distributed because we take just the sum, okay, divided by n. But the difference of the sum and something else, like square, that's something different, and that something different is now something that we know that it is chi-square. So now we can use chi-square to test this variance now. So now the hypothesis is one of this form. Okay. So we are trying to say whether the variance is less than or equals or greater than or equals to some value that we believe. Right, and we can, if we believe it is smaller than that, then the alternate hypothesis is that it is larger. So if in that case it would be yeah, that one, the right tail test. And again, we can replace that by equals or greater than or equals. And then we have to flip the corresponding signs to not equals and less than or equals to. So this will look like the original hypothesis test with mu and p, except we use different formulas. We use different test statistics to get a value, and that test statistic is just as simple as that. And so we have n minus 1. Right. Also here we don't take the sum, because that sum is already here. Right. We don't see the sum here, because that sum is already up there. Right. Because if we expand the s, that is exactly the variance. So that actually has like n minus 1. That is the actual variance. Okay. So this formula has a sum, but just we take the sum already and get that single s square value. Okay. And you can see that this n minus 1 will cancel out at the end. But anyway, once you get the s square from the sample, you can just you can plug this into this formula to get this chi-square. Again, we have 3 parameters. We have n, the sample size. We use n-1 because it would. We want that to cancel out with the bottom one. We have the sample variance, the variance we get from the sample, and we have the population variance. The population, this thing is the thing that we believe. Oh, actually, that should be the zeta naught. I see the thing on the right hand side. So for example, oh sorry about that. Yeah, let's go back first. Okay. So we can just use that, and once we get number, let's say we get 6.2, then we use this 6.2 again, just to repeat the process to get a p value. Okay, less than or greater than, depending on which side. Oh sorry, for the chi-square is always less than. Oh sorry, chi-square is always greater than. Okay. And then we use the p to compare that with alpha and again make a decision. So let's go back to this raw text. Let's not read it. Like if you have time, pause and read it. That's fine. I read it for you. So this is an example of the post office, which I believe no one goes there anymore. I don't know. I don't. I haven't been there for 3 years already. Right, let's say you go to a post office, and post office usually have a long line. Yeah, that the line there. Okay. So you want to see if people wait in the line for too long. Right, and yeah, maybe people complain and they say that they wait for 7 minutes, which is not that long if you look at all the shops. But yeah, let's say people complain that the thing is 7.2 minutes. Oh, sorry. If people complain, like, and the post office believes that the number, the standard deviation for that is 7.2. Okay, so that means this is the population. So from that we can immediately say that the sigma square is 7.2 squared. Well, again, we have to be careful whether this number is the standard deviation or the variance itself. In this case, we are given the standard deviation, so we have square to get the variance. And then we perform an experiment. Like we take samples, 25 customers, and they have different wait times, maybe 1, 2, 3, 0, 10, -3. Oh, sorry, not minus. You cannot wait. You cannot wait a negative amount of times. Yeah, so the result is in, and we get 0.5. Right. That means the variance. Okay. Usually we get these various numbers, right? And then we crunch them to get a single standard deviation. In this case, it means that the standard deviation is like is 3.5. It is from the sample. And since we are conducting a chi-square test for variance, we square that up. Right. So now we have these two numbers, and I think that that's all the information we need to know. Oh, we know 25 customers. Okay. And then we compare that with the 5% test. In other words, alpha is 0.05. We believe the wait time is 7.2 minutes. The standard deviation is 7.2 minutes, but the sample says it's 3.5. So we have to say if that deviates too much from what we believe. So let's go back and we have again first start with the null hypothesis. In this case, the null hypothesis is that the sigma square is actually, I think the belief is. Oh, let's say we test for that. We believe it's at least 7.2. We believe it is that long to wait until you are served in the front of a line, at the front of a line. That means the alternate one should be less than. Okay, so that's all done. Now what's next? Next is we have to identify what information we need. We need n, we need s square, we need sigma square. Do we have them all? Yes. So let's use them. So now you know the chi-square is n minus 1 times s square divided by sigma square. What is n? N is 21. Oh sorry, so 25 minus 1. What is s square? S square, it is the simple one, which is 3.5 square. And the sigma, what we believe, what we are trying to test is 7.2 square. And this thing will give us some number. So let me see what that number is. Chip. And that number is... I'm sure you can look at your notes just faster, but that number is... yeah, 5.67. Nice. So now we get a chi-square. That's the first half of the problem. We get chi-square now. The second half is the same as to previous lectures. And the second half is we compute for the p-value. What is the p-value? The p-value is that it is too small. And get the number of 0.00042. It's so damn small. Which agrees it again, but the intention, the intuition. Okay. We believe it's 7, but the actual is 3.5. Like that's pretty a pretty large gap. Okay. And since p is less than alpha, because alpha is 0.5, and that's like 0.00042. Since that is less than alpha, then that means we reject h now. Okay. So we say that okay, 7.2 is too long. We don't think that standard deviation is too. We don't think that the standard deviation is greater than or equals to 7.2. And we are done. Okay, the last. Okay, let's take a break and continue with the last two.